Hi, engineers. Ever wondered if your JavaScript skills are truly interview-ready? Imagine facing two of the most common coding challenges under real pressure. Could you nail them on the first try, explain your thinking out loud, and hit optimal O of n and O of log n time complexities without a hitch? That's exactly what we're tackling today. First up, add binary. We'll use 2 pointers starting from the right, manage carries smoothly, and output a clean binary string result. Second, search insert position. We'll implement a proper binary search to pinpoint the exact index or insertion spot in a sorted array. You'll spot the key patterns, sidestep common pitfalls, and get the precise phrasing to impress any interview. Ready to test yourself?
So, here's the problem. Given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would be if inserted in order. You must write an algorithm with O of log n runtime complexity. Let's rephrase it in plain English so it really clicks. We have an increasing list. If the target exists, give its position. If it does not, give the slot where it should go to keep the list sorted. First, let's set up 3 example inputs for later tests. We create a variable named nums and set it to the list of 1, 3, 5, and 6. Then, we create a variable t1 and set it to 5. Next, we create a variable t2 and set it to 2. And we create a variable t3 and set it to 7. Here's the warm-up approach for sanity, linear scan. We will write a simple O of n version first to lock expected behavior, then switch to O of log n. We create a function named searchInsertLinear that takes 2 inputs named nums and target. We will return a number. Inside the function, we start a for loop. We declare I equal to 0. The stop rule is I is less than num's length. The update is increase I by 1 after each round. Inside the loop, we create an if statement. The condition is nums at I is greater than or equal to target. If that condition is true, we return I. When the loop finishes, we return num's length. Why this helps? It gives the correct index or insertion point, just not an O of log n. Let's test the linear version. We write a console log of searchInsertLinear of nums and t1. Then, we write a console log of searchInsertLinear of nums and t2. And a console log of searchInsertLinear of nums and t3. When we run the code in the terminal, we should see the next results. For t1, the answer is 2. For t2, the answer is 1. And for t3, the answer is 4. Now the real solution, binary search in O of log n. The key idea is to maintain 2 boundaries, low and high. Check the middle. If the middle value is less than the target, move low to mid plus 1. If greater, move high to mid minus 1. If equal, return mid. If we finish the loop without a hit, low is the insertion index. Now, let's create a function named searchInsert that takes nums and target. We will return a number. Inside the function, we declare a variable named low and set it to 0. We declare a variable named high and set it to nums length minus 1. Next, we start a while loop. The condition is low is less than or equal to high. Inside the loop, we declare a variable named mid and set it to the floor of low plus high divided by 2. We create an if statement. The condition is nums at mid is strictly equal to target. If true, we return mid. Next, we create an else if statement. The condition is nums at mid is less than target. If true, we set low to mid plus 1. Now, we create an else block for the remaining case. Inside the else, we set high to mid minus 1. When the loop ends, we return low. Why low? It lands exactly at the first position where the target can be placed without breaking order. So, let's test the binary version. We write a console log of searchInsert of nums and t1. Then, we write a console log of searchInsert of nums and t2. And a console log of searchInsert of nums and t3. When we run the code in the terminal, we should see the next results. For t1, the answer is 2. For t2, the answer is 1. And for t3, the answer is 4. Here are some interview tips and pitfalls. Say your plan first. Binary search, low and high. Compare mid, shrink side, return low. State complexity. Time O of login, space O of 1. Avoid off by 1. Use while low less or equal high. Move low to mid plus 1. Move high to mid minus 1. Return low. Edge checks. Target before first gives 0. Target after last gives num's length. Let's start with the problem. Given two binary strings A and B, return their sum as a binary string. Let's rephrase it in plain English for better understanding. We add two numbers the same way we learned in school, from right to left, digit by digit. Each step adds bit A, bit B, and a carry. The current result bit is the sum mod 2. The new carry is the sum divided by 2, integer. At the end, if carry is 1, we put a final 1 in front. Here are some interview tips before we start. Say your plan first. Write to left addition with carry, O of n time, O of n space for the output. Then, call out edge cases, very different lengths, all zeros, and final carry at the end. Don't forget to mention Y strings. Numbers can be huge. We avoid numeric overflow and stick to character math. Let's start as usual. First, we set up two example inputs, so we can test later. We create a variable named A1 and set it to the text 1011. We create a variable named B1 and set it to the text 110. We create a variable named A2 and set it to the text 1111. We create a variable named B2 and set it to the text 1. Now, the beginner-friendly approach. Reverse, add, then reverse back. Why this way? Reversing lets us use a simple left-to-right loop with matching indices. It's easy to narrate and avoids tricky pointer math. So, let's start coding. We create a function named addBinarySimple that takes two inputs named A and B. We will return a string. Inside the function, we declare a variable named RA and set it to a split into characters and reversed. We declare a variable named RB and set it to be split into characters and reversed. We declare a variable named N and set it to the larger of RA length and RB length. We declare a variable named carry and set it to 0. And we declare a variable named out and set it to an empty list of characters. Next, we start a for loop. We declare I equal to 0. The stop rule is I is less than N. The update is increase I by 1 after each round. Inside the loop, we declare a variable named beta and set it to RA at I if it exists, otherwise 0. We declare a variable named bitB and set it to RB at I if it exists, otherwise 0. We declare a variable named a bit and set it to 1 if beta is 1, otherwise 0. Next, we declare a variable named bbit and set it to 1 if bitb is 1, otherwise 0. Then, we declare a variable named sum and set it to a bit plus bbit plus carry. And we declare a variable named resultBit and set it to sum modulo 2 converted to 0 or 1. We set carry to sum divided by 2, floored. We push resultBit into out. After the loop finishes, we create an if statement. The condition is carry equals 1. If true, we push the character 1 into out. Finally, we return out reversed and joined into a string. Now, let's test the beginner version. We write a console log of addBinarySimple of A1 and B1, and a console log of addBinarySimple of A2 and B2. When we run the code in the terminal, we should see the expected results, 10001 and 10000. Now I'll tell you some more interview tips before the optimized version. First, explain the improvement. We can avoid reversing by using two pointers from the end and a single while loop. Then, emphasize termination. Loop while I equals 0 or j equals 0 or carry. This avoids extra conditionals. And complexity soundbite. Same O of n time, O of n space for the output, less shuffling of data. So, here's the optimized approach. Two pointers from the right, no upfront reverse. Why this way? Fewer transformations, clean loop condition, and tight control of indices. Perfect for interviews. Let's code this solution. So we create a function named addBinary that takes A and B. We will return a string. Inside the function, we declare a variable named I and set it to A length minus 1. We declare a variable named J and set it to B length minus 1. We declare a variable named carry and set it to 0. And we declare a variable named out and set it to an empty list of characters. Next, we start a while loop with the condition I is at least 0 or j is at least 0 or carry equals 1. Inside the loop, we declare a variable named sum and set it to carry. We create an if statement. The condition is I is at least 0. If true, we add 1 if a at I is 1, else 0 to sum, and then set I to I minus 1. We create another if statement. The condition is j is at least 0. If true, we add 1 if b at j is 1, else 0 to sum, and then set j to j minus 1. We declare a variable named bit and set it to sum modulo 2 converted to 0 or 1. We set carry to sum divided by 2, floored. We push bit into out. When the loop ends, we return out reversed and joined into a string. Now, let's test the optimized version. We write a console log of add binary of A1 and B1, and a console log of add binary of A2 and B2. When we run the code in the terminal, we should see the expected results, 10001 and 10000. Why are both approaches correct? Both do right-to-left addition with carry. The first reverses to simplify indexing. The second uses pointers to avoid reversing. Both handle different lengths and a final carry. Time is O of n, where n is the longer string. Extra space is O of n for the output string. Here are some common pitfalls to avoid. Mixing characters and numbers mid-step. Always convert 0/1 to 0/1 before adding. Forgetting to append the final carry. Building the result left to right without knowing the final carry, which complicates string prepends. Push to a buffer and reverse at the end. Now you're 1% smarter. The cheat code is consistency, so keep boosting your brain. Make it your daily routine, and you will nail your next interview. Same rhythm tomorrow at Code Crack Interviews.